So tonight we're going to be talking about the integration by parts method for finding antiderivatives. As you recall, first method we chose was, first method we learned was just that you would use a formula. So you learned a bunch of formulas for finding antiderivatives. And then we learned just the other day about how to find antiderivatives using the U sub method. And tonight, like I said, integration by parts. And that will cover all three of the four methods for evaluating integrals, for finding antiderivatives. And the last one we'll learn in a later chapter. So for any antiderivative problems or evaluating definite integral problems, you're going to be using one of three methods for the time being: formula, U sub, or integration by parts. I should also point out that in that order is the way you should approach trying to figure out what's the best antiderivative, or what is the antiderivative. Start with formula, then go to U sub, and then when those two fail, then go to integration by parts. Okay? So I'll let you read this kind of introductory paragraph here on your own, but I wanted to start with basically a differentiation problem to kind of generate the formula for the integration by parts. And so if we differentiate the product y equaling u times v, where u and v are both differentiable functions of x, then we get, using the product rule, dy dx equaling u dv plus v du, throwing out the dx's by multiplying both sides by dx. We can write it a simple way like that. We've seen that many times. Okay, and then though, we're going to integrate all three parts. When you integrate dy, well, first we're going to rearrange the terms. If we subtract v du from both sides, we would get that, and then moving the integral of dy over to the right side, we get the integral of u dv equaling integral of dy minus integral of v du. Now, here's the thing. We already know what this is, the integral of dy, and that is just y. When we integrate dy, we get y. Did that in the last section. And then y, though, was defined to be u times v. So that's where we get this formula. This is the formula for integration by parts. And get a nice little box down here. And noticing here we have ultraviolet voodoo. Let me explain that. You may have heard that from if you have a friend that has already taken this class. But notice that you're integrating a u times a dv. Okay? Well, the formula is that on the right side of the equal sign you get the letters u times v. That's the ultraviolet. U times v, ultraviolet. And then we have v du, so that's the voodoo, ultraviolet voodoo. And there's always a minus sign right there. Okay, so the formula always has a minus sign. If you can remember the minus sign and ultraviolet voodoo, ultraviolet voodoo. Okay, so you can remember that. Say it as many times as you need to, but you need to remember this formula. And the purpose of the formula, just so you know, is sometimes we get an integral, an integrand that poses a challenge for us to integrate it in its current form. And so what we do is we switch the u and the dv to the v and the du, making it easier. So again, that's the goal here, is to make our lives easier in such a way that we can actually use maybe a formula for finding the antiderivative of v, whereas we wouldn't have a formula for the u. And we're going to do some examples so that you can see how it works. So let's go ahead and get the page 103 out. Okay, so here's our 103. Got that. Yeah, so we've got this nice box up here at the top reminding us of what the formula is. So we have the formula here. I also want you to write the acronym LIPIT. Okay, make sure you spell that right. LIPIT is, like I said, an acronym, and it's going to help us determine what to let u be equal to. Okay, so let me explain. Just like when you guys were learning the u sub technique, if you choose the wrong function for u, then you start having problems and it just won't work. You won't be able to find an antiderivative if you choose the wrong function, okay? Or the work gets so complicated it's not worth it. So this acronym here, LIPIT, helps us keep in mind what order in which we're looking for functions within our integrand. So if we look at this first example here, x times cosine x, we've got a polynomial function in x, and we have a trig function in cosine x. Okay, so let's look at the acronym and then we'll look at how to do this, how to find our antiderivative here using the integration by parts. The L stands for logs, logarithmic functions. If we have any logarithmic functions, that's what u would be equal to first, okay? And then the I stands for inverse trig, inverse trig. P stands for polynomial. So just like you learned PEMDAS, the order of operations, this is an order in which you're going to look for functions to let u equal. The E stands for exponential, exponential, and the T stands for trig, so any trig functions. Don't get that confused with inverse trig, that's what the I stands for. Okay, so if you read this down here, we've got, we're trying to use integration by parts to set up a chart here, and we have a u du here and a v dv. What does this mean? There's three pieces of information that must be placed into the u and the dv slots. We've got an x, we've got a cosine x for this particular example, and we have a dx. Okay, so the dx is always going to go in the dv slot. Okay, let me put that so you can see it. So the dx is always going to be right there. Okay, let's put the x. If you look at the order here, what are we gonna let u equal? Well, we don't have any logs, no inverse trig, but like I said, the x there is a polynomial, so the x is going to be what we let u equal. Okay, and then what does it say here? And the cosine x in the dv slot. So whatever's left over gets placed right there next to our dx, and notice that we have our u dv. Okay, u dv. Okay, and then so we have that, and if we differentiate both sides here, so we're looking at u equaling x, du on the left, and dx on the right. Okay, well, if our dv is cosine x, then dx, then what would our antiderivative of cosine x be? Well, we can see it right down here. The antiderivative then would be the sine of x, because the derivative of the sine is the cosine. All right, good. And so, if we, I guess the whole example, first example is written down here anyway. Notice that u times v. So basically, we're doing this. We're rewriting our u dv in terms of u times v. Okay, so this is the whole formula. So we're putting this into practice here. Can I span back here? No, I don't think I can. I don't think you can see both, but maybe u dv. So we have the integral of u dv, integral of x cosine x dx. Okay, that's equal to u times v. Well, what's u? U is x. Okay. And what's the v? Well, the v is sine of x. Okay, so you multiply x times sine of x, and then you have a subtraction symbol minus the integral of v du. Well, what's v? Well, v is sine of x, and du is dx. So it takes about probably about 7 minutes shorter to actually do that without explaining it. So it's a lot shorter when you when you don't walk it through step by step. You just kind of do it. You set up the chart, and you find your u, v, du, and dv, and you put them into this formula. Okay, so we have ultraviolet minus voodoo. All right, and so we have to finish it up though, because now noticing that we know the antiderivative of the sine of x, and the antiderivative of the sine of x is negative cosine. So what we have here is x sine x minus negative cosine x. And then don't forget about the plus c. That's where we get that right there. Now, if you wanted to take the derivative of this function here, you could determine that the derivative is the derivative of x sine x plus cosine x plus c with respect to x. If you do the work, I'm not going to do the work now, but the derivative of that function is x times the cosine of x. Okay? So that checks out. Alright, well, let's go ahead and take a look at the next example. Using my answer key on part of that, so let me bear with me here. You know what? I'm going to start a new video for this next example. So we'll start a new video for examples 2 and 3.